Hello and welcome to my presentation regarding the modeling and simulation in filtration with Geodik 2023, the latest and greatest features. My name is Mehdi Azimian from Mastermarket GmbH. For today's presentation, we have 5 highlighted topics as the following. The first topic is the new capability in Geodik to simulate the coalescence of droplets. The next topic is the modeling of cylindrical pleated filter elements with Pleat Geo module and the updated graphical user interface. The third topic is the automation in multi-scale filtration simulation. The next one is about the improvements in simulation of electrostatic effects by implementing the electrostatic charge decay model in Geodik. And last but not least, the possibility to run Geodik in cloud to accelerate the simulations and to reduce the computational time. First, we start with the new capability in Geodik to simulate the coalescence of droplets. The goal here was to increase the efficiency of droplet separating filters, or so-called coalescers, and reducing the pressure drop of the coalescers through the experimental and computational development of novel filter media made of bicomponent fibers. Mastermarket task here was to create and implement a model to describe and simulate the coalescence phenomenon in Geodik. This was investigated and conducted in the BIGOFIL project. BIGOFIL Cooperation Project was a publicly funded project. BIGOFIL stands for Bicomponent Fibers for Gas-Oil Filtration. In Geodik 2023, the new capability to simulate the coalescence of droplets is implemented and provided. The coalescing filtration is the separation of two phases, for example, the removal of oil or water droplets from a gas. Designing and optimizing new innovative cross-section shapes for fibers as bicomponent fibers, as shown here in the left image, in order to manufacture optimized fibrous coalescer media, as shown in the middle image, for the end use as a coalescing filter element, shown here on the right side, were the steps carried out in this project. As you can schematically observe in the middle image, when aerosols are injected into a media and more aerosols are filtered, the coalescence occurs among the aerosols contacting each other. And when the size and the corresponding mass of a coalesced droplet increases, then this droplet may be detached and discharged from the outlet as soon as the gravitation force becomes larger than the adhesive forces between droplet and fiber. As you can see here in this screenshot, we have a new tab as coalescence tab under fitting media module. And here the user can insert different contact angles for different material IDs. Besides that, the reentrainment and drainage options can be activated and adjusted accordingly based on the application. In this video, you can see one of the primary coalescence simulations on single fiber as more and more droplets are added, and then they grow and form a bigger droplet. The video on the left side shows the formation of a larger droplet with a contact angle of 100 degrees. And on the right side, a droplet is formed having a contact angle of 10 degrees. So we have these two cases of hydrophobic and hydrophilic fibers in this slide. Here we show no droplet detachment mechanism, but the detachment mechanism is also available in the current Geodik version, which I will show in the next slides. In this slide, we show a fibrous media modeled with the Fiber Geo module. The media is modeled as a coalescer filter media from Alstom with application for oil removal from compressed air. The media is made of fibers with 3 different diameter size distributions. First, the flow and filtration simulations are conducted to compare and validate the simulation results with the experimental data of Alstom, shown here in this table. The initial pressure drop was measured by mean flow velocity of 5.32 cm per second, and the filtration efficiency was measured for aerosols with a mean aerosol diameter size of 0.3 micrometer at a mean flow velocity of 5.2 0.32 centimeter per second. As can be observed in this table, there's a very good agreement between simulation results and the experimental data by Alstrom. In this video, the oil aerosols, which are in the airflow, are tracked through the media, and the filtration of aerosols, the coalescence and detachment of aerosols are simulated. When aerosols are injected here from the top into the domain, and more aerosols are filtered, the coalescence occurs among the aerosols contacting each other, and the size and shape of new generated aerosols will be defined. And as mentioned, when the size and the corresponding mass of the coalesced droplet exceeds from the threshold value, then this droplet can be detached and even can be discharged from the domain outlet. The next topic is the modeling of cylindrical pleated filter elements with Pleat GeoModule and the updated graphical user interface. In Pleat GeoModule of Geodik, besides the rectangular pleat option, which was existing already, now we have a new option as cylindrical pleat. This submodule is implemented to design and model cylindrical pleats, and it's ideal for automated case studies to optimize pleat form and counts. And of course, the user is capable to save STL files for exporting into other software if it's necessary. As shown here, this is a screenshot under the cylindrical pleat command of Pleat Geo. By inserting the geometrical parameters related to pleat shape and pleat count, number of layers and details of each layer in Pleat Geo user interface, we can model or generate the cylindrical pleated elements and save this structure as a GDT file. Besides the classic cylindrical pleated elements, there is also the possibility to model M-pleat cylindrical elements. So as you can see here in this screenshot, you need to check the M-pleat pattern and then adjusting the rest of the parameters regarding the pleat shape, number of pleat layers, and information that you can adjust here. For the starting point or as a basis, we need initially the CAD data of the filter geometry. So any complicated filter geometry with housing can be imported. And when you would like to investigate, for example, the effects of pleat count on flow and filtration characteristics, the existing cylindrical filter element, which you can see here at the left side, 40 pleats shown with red color, can be substituted by other variations. For example, on the right side, you see a red cylindrical pleated element with 60 pleats, and then the following simulations can be started. The process can be also automated using Python scripts when the user is interested to investigate many variations. For filter or for the macro scale modeling and simulation, the Geodik workflow is now improved to provide a more user-friendly and efficient approach. With this feature, the effects of pleat geometry and the number of pleats on the flow and filtration characteristics can be investigated in a very fast and efficient way instead of using external CAD software. So in this animation, you can see here when we change the pleat count, the inner and outer diameter, the height of the pleat radius, we can directly do this in Geodik using Pleat GeoModule, and you don't need any, let's say, external software, and this saves a lot of time to prepare the different geometries for optimization studies directly in Geodik. When different geometries having different cylindrical pleated elements are modeled, the next step is to run flow and filtration simulation and, let's say, visualize the results. Here is an example. We can observe the flow velocity distribution, the left side, and on the right side the pressure distribution field visualized here. The Fitedict user interface in Geodik 2023 is updated, and now we have the complete filter. With the complete filter we mean the filter with housing and also the cross-flow simulation capability, for example for membranes. Both of these two commands are now available under Fitedict module, and moreover, as already shown in the previous slides, the coalescence tab is now also available under Fitedict media module. The next topic is the automation in multi-scale filtration simulation. For the simulation of filters on meso or macro scale, we need the detailed results computed from simulation on resolved scale or on micro or nano scale. What we know as an introduction is that there's an increase in the trend to use fine micrometric or even nanometric fibers in filtration. When we consider a multi-layer, or here as shown, a two-layer filter media with a large difference in the fiber diameters of each layer, then the simulation of both layers in one simulation run becomes quite challenging. This is mainly due to the different resolutions which are required for each layer to have a representative domain size. And in geodetic, a multi-scale approach helps to overcome the issue and to accelerate the simulations by drastically decreasing the number of total voxels in the computational domain. So as you can see here on the right side, when we consider a two-layer filter media, on the top coarse layer, at the bottom a fine layer shown with red color, the fine layer can be modeled as a porous simple plate with the same permeability and same flow and filtration characteristics that we already obtained from a first step simulation on the fine layer. And then in the next step, we can consider this fine layer as a porous layer and then running a simulation on both layers with, of course, much less total voxel count. For a correct and precise simulation on an unresolved scale, a series of information or details from a resolved simulation is essential. These are listed here as, first of all, the permeability of the clean media, then the thickness of the media, the filtration efficiencies per particle type, the maximum particle packing density for cake and depth filtration, and also the maximum flow resistivity for cake and depth filtration. In previous geodetic versions, the user had to manually compute most of these parameters and insert them into Fitedic element. However, these parameters are now automatically computed and reported in Geodetic 2023 after running a Fitedic media simulation. As you can see here, you get a table from a Fitedic media simulation, and you can use or insert this information directly for a Fitedic element or an unresolved simulation case. And this saves, of course, a lot of time and accelerates the procedure. The fourth topic is the improvements in simulation of electrostatic effects by implementing the electrostatic charge decay model in geodetic. For simulation of electrostatic forces, we have currently three options. The first option is what can be found under the Fitedic graphical user interface, where we can adjust the surface charge and also the particle charge. The limitations are that the user can't assign different charges for different constituent materials, and also can't assign the location of charge. For example, if you want to have only for the electrostatic forces only for certain layers, or only, let's say, z-coordinate dependent charges. And with the second possibility that we have using expert settings, one can overcome these limitations. So with these expert settings, we can assign different charges for different materials, as shown here in this screenshot. And the third option is the ESF solver, which we can provide this to users, and the user can implement or modify any different model in geodetic. Expert settings, there has been a new significant improvement in simulation of electrostatic forces in geodetic. That is the implementation of the electrostatic decay model. It's known that when the particle deposits on the fiber surface, the charge on the surface of the voxel occupied by particle is reduced and removed, resulting in a declining electric field. As shown in this screenshot at the bottom, expert settings are implemented to make the surface charge of filter medium decay with an equation provided here, where XCI is the filter surface charge at the batch I, XC0 is the initial surface charge, A is the decay factor, and the variable lambda can be time, deposited dust mass, or dust solid volume fraction. By applying the electrostatic decay model, we could significantly improve the quality of simulation results. Here we can observe the old and new geodetic simulation results when comparing with the experimental data provided by FITI Testing and Research Institute. The measurement shows that the penetration increases at the first stage, It means the electric field weakens and filter efficiency decreases. But when more and more particles are caught and many or most of the pores are filled and filter cake builds up, the filter efficiency increases again. So the electrostatic field is changed with increase in particle loading. And this can be observed here on the right side, that the simulation results can also predict this behavior. Last but not least, only some brief facts about the possibility to run Geodik in the cloud to accelerate the simulations and reduce the computational time. There is the possibility to use the cloud capabilities. There are currently several cloud solutions. The Master Market company currently offers two main solutions. First, the remote desktop usage with Amazon Web Services. And the second option, the user interface for parallel job execution with KaleidoSim. And as you can see here, in this screenshot, the Geodik 2023 includes a Run in Cloud button so that the user can set up all cloud settings and start simulations. For example, here we have different flow rates for different filter elements with different number of pleats. So ones with 54 and ones with 56 pleats. And when running the simulations, the user can inspect current status under show log. And when the simulations are done, the user can download the results and manage the project. Here we can observe the simulation results for different flow rates. So 5 different flow rates for filter elements with 54 and 56 pleats. So in total 10 simulations. With this, we obtain valuable information and perform parameter studies or optimization study very efficiently. The simulation time in the sequential way was about 240 hours using 16 parallel processes. On the other hand, by using cloud, the simulation time in a parallel way was about 24 hours using 16 parallel processes. So with this, I come to the end of my presentation. Thank you very much for your attention, and I look forward to your questions or comments.